Merci beaucoup, Begoña, merci beaucoup. Donc maintenant, on a cette vision générale de l'eau, de l'air, de l'alimentation, de la lait maternel. Maintenant, c'est le moment, par exemple, de préciser sur, par exemple, the guidance on sampling, screening and analysis of persistent organic pollutants in products and articles. Donc maintenant, on va vers le produit. Et c'est le tour de Roland Weber qui va faire la présentation online. J'espère qu'il va être connecté.
Okay, good. Yeah, so good day, everybody. Thank you very much for inviting. My today's talk will be monitoring of POPs in products and the introduction to the Stockholm Convention draft guidance on sampling, screening, and analysis of POPs in products and recycling. When you look to Article 6 of the Stockholm Convention on POPs, which requires parties, among other things, to develop strategies for identifying stockpiles, products, and articles and waste containing POPs. So identifying POPs in products and articles is crucial for their environmentally sound management. And it is at the same time a significant challenge for parties, including Tunisia, but also for the POP Reviewing Committee. The challenge is identifying chemicals in products and articles. One is because of technical limitations, the cost of monitoring, the limited expertise and knowledge, and also that there is a lack of labeling of articles. So therefore, the Stockholm Convention Conference of Parties acknowledged in the 11th meeting these challenges and urged parties to implement Article 6 effectively. So here, the Conference of Parties means the countries requested to the POP Reviewing Committee to explore options for identifying POPs in products and articles, and they were asking to develop a report on this. And this report was just published as an information document at the Conference of Parties in this May, 2 weeks ago. So this document highlights that it recognizes the complexity of identifying POPs in stockpiles and products and articles in many countries and regions, especially in low and middle income countries. And it notes that the report identifies challenges in identifying POP stockpiles, products, and articles, including financial and technology capacity challenges, global regulatory challenges, complexity in value chain, and the lack of disclosure of information on chemical content in articles and products throughout the value chain. So in the first presentation this morning, Kay from the BIS Secretariat highlighted and showed this complexity in the value chains and let's say the understanding of how the flow of POPs in products is with this complex value chain. Also, there is a lack of traceability and transparency in this value chain. And one big issue is regulatory limits. At the moment, when we look, for example, in Tunisia, for most of the industrial POPs in products, probably you do not have a regulatory limit. Yeah. So therefore, when we talk about monitoring POPs in products, the first question is at what concentration we should monitor. Yeah. Monitoring make only sense when there is also a limit and restriction and regulations. So I have put here a slide from the European Union on the POP regulation with the different limits. And you see on the very right side, here you have the so-called Annex 4 values, limits. So this is for waste. Yeah. And even more important, in Europe, over the years, so-called unintentional trace contaminant limits have been developed. And these are limits for products. And only when you have such limits, then you can make reasonable monitoring and you know at what levels you need to monitor in products, that you can tell this article is a problem in respect to our legislation or not. When we look to our 37 POPs group, meanwhile, we have many POPs listed, which are mainly used in consumer products, often as plastic additives. We have 5 brominated flame retardants. We have 3 chlorinated flame retardants. Begonia just has presented on the PFAS, but let's say she has presented on air and water, but the first part is PFAS in products. So PFAS are also mainly in products, including, for example, textiles or furniture and so on. And some of these POPs are high volume chemicals, including, for example, from the PBDEs, the decap bromodiphenyl ether, the hexabromocyclododecan, the short-chain chlorinated paraffins, the medium-chain chlorinated paraffins. So they have been produced in millions of tons in the past. And you have seen from the presentation of Dr. Malish in human milk, how, for example, the chlorinated paraffin levels are increasing in human milks globally, and will be soon the largest POP monitored in human milk. There's also now the first non-halogenated UV stabilizer, UV328, which have been listed, and soon the polybrominated dioxins and furans and mixed halogenated dioxins and furans will be listed, which are also related to products and articles. And the major of these POPs, the major share is in plastic. And this plastic is mainly used in electronics, in transport sector like your cars, in the construction sector. And overall, at the same time, these 3 sectors make around 30% of all plastic used in production. And when you look to Tunisia and to your total plastic stock in Tunisia, these 3 sectors have likely more than 50% of all plastics in your country. This is a view of the sectors: construction sector, electronic sector, and the transport sector. And here on the left side, you see the range of POPs they include. The ones which I marked in yellow, these are basically more or less only in these 3 sectors present. But also, for example, short-chain chlorinated paraffins and medium-chain chlorinated paraffins have their major use in plastics in these 3 sectors. But when you look into more detail, only a share of the plastic in these major uses contain POPs. What you see in this figure is first the different polymers. This means polyethylene, polypropylene, polystyrene. And on the left side, you see the different application area. For example, here for packaging, you see packaging normally don't contain POPs. I have here included in the red circles the share of plastics which I consider contain POPs, and also roughly the share of that product. When you look here to the building and construction sector, you see, for example, the polystyrene extruded and expanded polystyrene, which is used in insulation foam. A large amount of this foam in the past have been flame retarded. So therefore, we know here this product really contain a large share POPs. But for all others, it's only normally a relatively small fraction. And for most of the spots, for example, here for automotive, you see, I did not put a red spot because there are any data. So this means the use frequency of POPs in products is often unknown. It can be high, like I showed for the EPS, XPS in buildings, or low. And this needs monitoring, and actually it needs more monitoring. I will introduce in this presentation also some case study. But first, coming to the guidance, to the Stockholm Convention guidance, here you have an overview of guidance documents which have been developed in the frame of the Stockholm Convention, a range of inventory guidance. One of them, a new one, is the sectoral POP inventory guidance, which are addressing the three sectors: electronics, buildings, and transport. And here is the guidance on monitoring of POPs in products and recycling. So the background of that guidance was that in 2009, for the first time, POPs which are used as plastic additives or otherwise in consumer goods have been listed. That was at that time polybrominated diphenyl ethers, tetra to hepta BDE, which are also used in electronics, vehicles, and buildings, and also PFOS have been listed in 2009. So at that time, the Secretariat of the Basel, Rotterdam, and Stockholm Convention saw that monitoring of products in the consumer market and in stock and use and waste will be needed. And also some monitoring of electronics is needed to better understand the extent of contamination of plastics also in end of life and the risk of recycling. Because when the PBDE in 2009 were listed, the Conference of Parties decided to make an exemption for recycling because it was unclear if not whole recycling areas would need to stop when listing PBDEs. So therefore, at that time, a guidance document was needed that support parties in the monitoring of PBDEs and PFOS in products and also give information on PBDEs and PFOS in products. So therefore, the Basel, Rotterdam, and Stockholm Secretariat initiated in 2010 a monitoring activity for PBDE in cathode ray tubes in Nigeria that was at that time financed by the Norwegian government. And Professor Osibanjo from the Basel Convention Regional Center in Nigeria and I were tasked to guide and conduct the monitoring study. Additionally, I was tasked to develop a guidance document on monitoring PBDEs in electronic waste plastic and also PFOS in products. So the first guidance which I developed in 2010-11, this included finally the PBDEs, the PFOS, and also we decided to include pentachlorobenzene and hexachlorobenzene, which pentachlorobenzene was also listed in 2009. And by this, to have a monitoring guidance which includes the three major halogen groups: brominated, fluorinated, and chlorinated POPs in consumer products. This guidance was then extended in 2016 and 17 to include the POPs listed in 2013 and 15, including hexabromocyclododecan, PCN, pentachlorophenol. And the guidance was updated in 2021 with then the POPs listed in 2017 and 2019, including also short-chain paraffins and PFOA. So when we developed in 2021 and updated the guidance, we also included the circular economy and recycling aspect in the guidance because we have now a global push to circular economy. And also when we are moving to circular economy, there need to be even a better control of POP in recycling. Yeah. So at the moment, the recycling rates in Tunisia are probably also relatively low for plastics. But now you certainly will have governmental activities to move to more circular economy. And when you move to more circular economy of plastics, you need to think on the fate of POPs. And this is one reason for that guidance. So here, this guidance provides guidance on monitoring, including sampling, screening and analysis of POP content in articles and products listed from 2009 to 2022. So guidance is provided here first on the different articles and products possibly containing POPs, to develop strategies for monitoring of POPs in products and circular and recycling streams, on inventory development aspects, and also to determine emission and impact factors for major material flow. And when we look into detailed chapters of the guidance, you see here the fluorinated POPs are addressed here in chapter 3, brominated POPs, PBDEs, HBCD in chapter 4. We have one chapter about polychlorinated naphthalines and PCBs in products and recycling, one chapter of short chain and medium short chain chlorinated paraffins, one chapter about pentachlorophenol, one chapter because pentachlorophenol is, for example, used in leather, in textiles, and in wood, so also major product categories. And also we developed one chapter about all unintentional POPs in products, including dioxins, PCBs, hexachlorobutadiene, pentachlorobenzene, PCNs, and hexachlorobenzene. In chapter 2 of the guidance, at the start, there are general consideration and cross-cutting issues. This includes also capacity building of monitoring in low and middle income countries, a section on quality assurance and quality control, a section on international standards for analysis of POPs in products, and one section about certified reference materials and interlaboratory studies. So when you are thinking in Tunisia, for example, to develop monitoring of POPs in plastic, the first thing is really to establish that and to have a high quality monitoring. And for example, for this, you need certified reference materials and interlaboratory studies, where you then finally can conclude that your laboratories are appropriate to do such monitorings. The monitoring guidance has a step-by-step approach to monitor POPs in articles and products, and these steps are elaborated for all the major POP groups in the individual chapters and annexes. So it is a 5-step approach. The first step is a survey of products and recycling streams containing POPs. You can do in Tunisia. The second step is the sample collection. The third step is screening of the products. I will come to details on that. The step number 4 is quantification of POPs in products. And step 5 is documentation and reporting. Now I go through the 5 steps, starting with the first step. That's the survey of products and recycling flow, possibly containing POPs. Before collecting samples, a survey is needed to conclude and to preliminarily determine major consumer products in use and reuse in the countries that might contain POPs and in which your government or your research institution is interested. Also, in this step, you can look to material flows known to possibly contain POPs, which are used in recycling, for example, electronic waste plastic, or recycling of polyurethane foam, or recycling of carpets or textiles or rubber. And here in the guidance, we have in Annex 1 all major product groups and major recycling streams for the individual POPs. So you see here in Annex 1, for example, 1A, we have the PFAS and related compounds in products, then Annex B for the brominated POPs, and so on. And you see that this annex alone is nearly 30 pages. Yeah. So here, when you are thinking to develop such a monitoring in your country, you could have first a look to these 30 pages and see, okay, what could be useful or not useful. And then you could select what you find interesting for your countries. So this is just now Annex 1 here for the PBDEs. You see here a long list And all these individuals like electronics, second-hand electronics, e-waste plastic, there's always a description and some background, yeah, on these different product categories. Then step 2 is sample collection. For sample collection, different stakeholders for the different consumer product categories might be contacted for input, for support, and possibly also for providing samples. Relevant stakeholders to be contacted for different POPs use. Sectors would be compiled in this phase. And also here the POP inventory guidance document, and also especially for the different inventory guidances can help you to find stakeholders. Sampling campaigns might be conducted by a research institution, possibly in collaboration with ministries or other competent authorities, or directly with the industry or waste management facilities and related recycling. Samples can also be collected, for example, by the customs at import or by competent authorities, such as factory control or consumer protection authorities. We have also included some good studies which describe different sample methodologies in different case studies. I will come later in the case studies to that. The third step is screening in the field or in the laboratory. As I showed you with the plastics, only a minor share of target products contain POPs. For example, less than 20% of cathode ray tube casings contain PBDEs. And also only a minor share of carpets or textiles contain PFOS, PFOA or other PFAS. So therefore, sampled articles can be screened for the presence of bromine, chlorine or fluorine in the field or in the laboratory to minimize the effort of analysis of samples. So such screening enables a relatively cheap and simple pre-selection of samples, and also screening helps to minimize the time and expenses in the laboratory. It does not make sense to measure any plastic which does not contain bromine for PBDEs, for example. The Stockholm Convention guidance for monitoring POPs in products gives an introduction to the different screening approaches in the sampling step. The guidance compile information on screening methods for bromine, chlorine, and fluorine in products and recycling, which can be used for sample pre-selection. Also, some instrumental screening methods for the individual POPs are described, which do not need the extraction and cleanup step, for example, pyrolysis GCMS. Yeah, all this is explained in the guidance. When screening methods are applied, it has to be ensured that the detection limit of the screening method is more sensitive than the limit required for the sampling. For example, if you have a legislation limit, for example, 50 ppm for PBDEs in waste or in a product, then of course your screening method need to be lower than this 50 ppm. Yeah, the same, for example, for PCB, yeah, for chlorine. What you see here, this is the different sections of screening methods for fluorine and organofluorine chemicals possible in products and articles. You see there are 11 methods described, starting from the very simple droplet test where you just put a drop of water or a drop of oil on a textile or on a carpet or on a furniture, and where you can understand from this droplet test if this material contain fluorinated compound or not, yeah, up to very complicated methods like NMR spectroscopy or certain high resolution methods for screening. Same here for brominated compounds. You see here in chapter 4.4, there are 8 screening methods for brominated compounds. Most of you might know the X-ray fluorescence, XRF spectroscopy, but we have also listed other methods where you could have a look at. For example, for sure, you also have FTIR spectroscopy in Tunisia, which you might use, and also, for example, combustion ion chromatography. Here, just a bit detailed to the XRF screening, because let's say that's so practical. So screening in the field or in the laboratory can be done with the XRF spectrometer. X-ray fluorescence spectroscopy can be used for detection of bromine in products with a quite low detection limit. It can go as low as 5 ppm. For the detection limit of chlorine, that's higher. Normally, it is higher than 100 ppm. Recently, also the first handheld X-ray fluorescence spectrometer has been on the market. So also now by this mobile, you can screen here products even in shops. But this XRF analysis is limited to the detection of elements. Yeah, it does not have the capacity to identify the chemical. But like I said, it is super for pre-screening. It only takes around less than 1 minute. Yeah, and after that, you can decide if this sample is interested to further analyze or not. If a sample is heterogeneous, for example, if an electronic product contains different plastic parts, then different parts need to be screened here with the XRF, which is also possible. It is non-destructive method, so even you might be able to go to shops and do some screening. And but the use of XRF instruments require a specific instruction for the operator, because you are handling X-ray. Yeah, so therefore, probably also in Tunisia, there will be a certain regulatory frame which you need to consider when you buy or handle such an equipment. Step number 4 is quantification. So where available, here for quantification, the guidance compile international standards for pop analysis in products and the related references. But for a number of product matrices, no international standards were available. So there I have looked if there are some robust methodologies from some research groups, so-called in-house methodologies. And we have also described for a range of products in-house methodologies, which are not international standards, but which are proven methodologies to analyze POPs in products and recycling. And the guidance further reference in Annex 2 to case studies. And also many of these case studies contain analytical procedures for the POPs in the respective matrices. So here I give you an example on sample preparation, extraction, and cleanup for the brominated flame retardants. So here is a dedicated section about preparation of polymers and plastic samples. Then on extraction of brominated flame retardants from polymers and plastics, extraction of PVDEs from flexible polyurethane foam, from HBCD in textiles. And this is quite complex and complicated, this method, yeah, because as you will see, plastic is a very versatile matrix. Different plastics behave different in extraction and cleanup, and therefore the preparation need to be adjusted and optimized. I have a friend who is doing this since 20 years, and every month he has some surprises in the cleanup and in the analysis. And care has to be taken that the polymers do not contaminate the instrument. So you deal with a full matrix, and it's easy to get here some of these oligomers into your instrument, and the result is that the GC column is crushed, or even the mass spectrometer might be contaminated. Yeah, so therefore a very optimized cleanup is important for this method. And the second is that when you deal here with samples which can contain up to 20% of POPs, you need to take care not to contaminate your whole laboratory, and also take care of memory effects in glass and in the analytical equipment. Normally, a room which is used for such products, normally the same room you cannot use to analyze low contaminated samples like food or environment or water. So here, then there are different methods on quantitative analysis of the individual POPs. So here you see also as example for the POP BFRs. So here in one section we have a measurement standard for the PBDEs, example of a GCMS setting, but also example of GC-ECD setting or LCMS setting for the instruments. And again, we have a full annex which includes for all relevant POPs in products a full analytical method for the instrumental analysis. Yeah, so here you see this annex is also nearly 40 pages. And for all the individual POPs, you have a full description of an analytical method. Yeah. For example, here for PBDE, you have one method for GCMS described, and also one method of GC-ECD described, or HPLC-MS method for hexabromocyclododecan. One example here just for the GC method for PBDEs. So you see the full temperature program is described, what type of column, what possible instrument, how to make the setting of the injector block, everything. And this instrumental setting we have from top leading laboratories from the world, a big share of them from Shimadzu Techno from Japan. So they were for several years the best laboratory in the world for interlaboratory comparison. Also, we have for all the compounds the detailed masses. So here you see the full masses for the PBDEs, including the quantification mass, the confirmation mass, but also the carbon-13 standard masses, so that you can do a full setup of an equipment for that. And we included for all the methods also a chromatogram. Here, for example, for the PBDEs, and I found it always very helpful. I also worked for 6 years in a research laboratory when I have a good detailed description, including also the chromatograms and the individual congeneers numbered. Here, for the short chain and medium chain chlorinated paraffin, we also have 3 methods described. One method, low resolution GCMS. This can be used also for low and middle income countries, this method with normal GCMS. Then we have one method with an Orbitrap, very quite sophisticated instrument. Dr. Malish has one in his laboratory. But in many countries in Africa, I'm not sure if there is any Orbitrap in whole Africa. And we have described LCMS method from the National Institute of Japan. And this method also allows the monitoring not only of the short and medium chain chlorinated paraffin, but also of the long chain chlorinated paraffin, which you cannot measure with the gas, with the GC. Also, we have 3 analytical methods for PFAS. We have described 2 LCMS methods. One is the method of the National Institute of Advanced Science and Technology from Japan, which at the same time is the ISO 21675 method you see on the right side. And also we described a GCMS method from Professor Francis Oraka. He made his PhD in Germany, but is since many years back in Kenya and is doing PFAS monitoring in Africa. One challenge here is that most PFAS related compounds, because PFAS and PFOA is just one compound, right? But the related compounds, for example, for PFAS are 165 compounds, and PFOA-related substances are more than 300 compounds. And for most of these compounds, no analytical standards are available, as Begonia already highlighted in her presentation. And recently we wrote a paper in which we requested of standards from industry because at the moment many products which are produced from industry are not available as commercial standards. But for example, when you look to pesticides and the EPA, all pesticides need to be given to the authorities in Europe and America, that the laboratories also can analyze these compounds. And in our paper, we propose that the same should be done for PFOS, PFOA, for the industry, and best for laboratories then globally. At the moment, there's just the total oxidizable precursor assay, where we can, let's say, also analyze and screen for the precursor compounds. And at least by this method, we can also cover and roughly estimate what is the amount of precursor compounds in a sample. Then in Annex 2, we have compiled best practice case studies, where available best practice case studies for monitoring of key product categories, possibly containing POPs, are referenced in Annex 2, where possible case studies or publications were selected, which are also open available. By inclusion of case studies, the guidance endeavors to provide information on already performed major studies and approaches used. So these case studies can be assessed with the view of selecting the most appropriate approaches and methodologies for screening, for sampling and analysis. But my recommendation is not just to repeat, so rather to add good and innovative new case studies. And I hope maybe in 1 or 2 years' time, we also see some good case studies from Tunisia monitoring POPs in products and recycling. So here in Annex 2, you see an overview on the case studies. Also, this is more than 20 pages. And here now I will show and go through the major sectors and show some best practice case studies. First for electrical and electronic sector. So that's actually the case study which we conducted in Nigeria in 2011-12. So at that time, we sampled cathode ray tubes in Nigeria, which contain the average most amount of PBDEs in electronics and electronic waste. So here 2 students, PhD students, sampled 380 CRT casings, and then they collected information on manufacturer, brand, model, serial number, year of origin, and we targeted televisions and computers from 1980s to 2006. Why? Because the aim was to understand the former use of the PBDEs which were listed in 2009. And this was commercial octa BDE and commercial penta BDE, and their production stopped in 2004. Yeah, that was the reason why we selected and focused on this. So here we also did then a pre-screening with XRF, and then in the second step, a confirmation analysis with GC-ECD and GCMS. So for the pre-screening, the CRT samples were prepared by cutting out a small piece. And these pieces, together with a PhD student, was sent to Germany, to Fraunhofer Institute, and they did the screening here in laboratory. But if Tunisia, if you have a XRF, you can directly do this screening in the field. But at that time in Nigeria, there was no handheld XRF in Nigeria. So therefore, the students cut out the samples and brought them to the laboratory here to Germany. So within 3 months, she did the screening and also the analysis. And here in Fraunhofer, that's actually the institute which is doing since 25 years monitoring of POPs in plastics of electronics. So they have developed a good methodology here, a dissolution precipitation method, where 0.5 gram of polymer is dissolved in 5 milliliter tetrahydrofuran, and then it's precipitated with hexane and filtered, and then with a specific dilution factor, which is also quite complex because such a plastic can include 20% of PBDEs, or it can contain 100 ppm of PBDEs. Yeah, and you want to understand and see them all. So therefore, also this is quite sophisticated, and you might need several injections. And like I said, plastic is a very difficult matrix to analyze with a high risk to contaminate your GCMS. And you really need to take care and have such a kind of a cleanup which is protecting your instrument. This is result from the study. So you see that a high share of these cathode ray tubes were flame retarded here in violet, yeah, purple. So you see that a large share of the computers here from Asia, also the computers from America, contain brominated flame retardants. Here for Europe, the rate was a little bit lower because our flame retardant standards are a little bit different. Yeah, but you see overall the regions were not so different. Yeah, we sampled from each region to understand if there is a difference. Finally, our conclusion was not a too big difference, but for Europe, the flame retardant use was a bit less. Also, when you see here this one in purple, so this were fully brominated flame retardant sample, and this one in green and in red, they contained brominated flame retardant at a level of 100 to 10,000 milligram per kilogram. And this concentration is considered only to stem from recycling and not from full application of flame retardant, because normally you need more than 3% of brominated flame retardant here in your television. And when we then analyzed the PBDE, we found that from the 380 samples, only 4 samples were intentionally flame retarded with commercial octa-BDE. But these 4 samples were already sufficient when you would mix the whole plastic, that this plastic is above 1000 milligram per kilogram and therefore above the low pop content. Yeah, 4 samples out of 400 samples. And 34 of the 380 samples, around 9%, contain deca-BDE in concentration between 617 to 230,000 milligram per kilogram. Also here, the average concentration would be nearly 4,000 milligram. This means 3 to 4 times above the low pop limit of the Stockholm Convention. Therefore, if you just mix these samples together, these polymers can only be for recycling after removal and bromine containing cases and separation. So most electronics consist of several electronic plastic parts, and often only a few of these parts are flame retarded. Therefore, some screening of plastic parts might be needed. I give you here one example. So when you look to the CRT televisions, often the casing is flame retarded, but here the stand, yeah, where the CRT is standing on, the plastic is normally flame retardant free because it's not getting hot. Yeah, and normally only these parts are flame retarded, which get hot. So there is one best practice case study for monitoring PBDEs in large and small electric and electronic equipment and individual plastic parts from UK and from Wales. So they screened plastic parts in fridges, and this showed that only a very few pieces and only in some fridges contain high levels of POP BFRs. And these were only the casings, the small casings of electrical and the compressor, and the electrical and junk box and the cable box. But the most outer major plastic parts like doors, side panels, trays, shelves, and so on, they did not contain any flame retardant and any POP. Yeah. Also, in other large household appliances like washing machines and dishwasher, only a few control boxes contained flame retardant, while all other major plastic components did not contain flame retardants. But this is actually really the only full-scale study which have done such a monitoring. And I think that more studies on monitoring individual plastic parts in electronics for POP additives are needed, including now also the new listed UV328 and Decloran Plus, and best with analysis of all flame retardants and not just a few target components. Then a second best practice study is from the Swiss authorities in 2008. They monitored 1,360 consumer products for brominated flame retardants, including electronics, building materials, and lighting equipment. The monitoring approach taken was also first to do a screening of products with the XRF, then to analyze with GCMS the bromine positive, which had more than 500 milligram per kilogram, and they analyzed PBDEs and other commonly used other brominated flame retardants. In bromine positive samples where neither PBDEs nor commonly used brominated flame retardants were detected, then a Swiss laboratory performed a non-target screening of new brominated retardant to understand what kind of flame retardants are used on the Swiss market. So the study showed that the PBDE content in products in Switzerland and likely Europe market in 2008 was already low. So from the 1,360 consumer product, only 17 samples, this is 1.3%, contain DKBDE above 1,000 milligram per kilogram. And only 2 samples, this means around 0.1% of the samples, contain commercial PBDE. Yeah. So you see only a very, very few samples in 2008. Yeah. And before you saw with the televisions from 1980s, 1990s in Nigeria, yeah, that there are a large share of the products were flame retardants with PBDE. So already in Europe in 2006, the ROS directive included the DKBDE, and therefore industries started to phase out. Yeah, this kind of information also is quite helpful for you when doing such monitoring. Overall, the Swiss market survey analyzed 1,900 components. This means also they screened different parts of plastics in products. In total, 470 components contained bromine above 500 ppm, and 214 samples were then quantified for the PBDEs. So here you see more detail of the results. 60 samples contained at least one of the target substances. Yeah, and here just a little bit on detail. When you look here to building materials, you see that in 2008, still a considerable share of the building materials screened, it were only 17 samples, but still around 30% contained DKBDE. Yeah, but the electrical devices already only 10%. Yeah, contained PBDEs. Yeah, for the automotive devices, it was only 7 samples. Yeah, none of them contained PBDEs. Yeah, what you see here in red is that other brominated substances, which were not at that time in the Swiss monitoring for general flame retardants. Yeah, and so you see this kind of monitoring is quite complex. You really need to do a good planning and thinking what you want to analyze, and then also how you want to screen for those where you do not know finally what kind of brominated or fluorinated compounds are there. This is still from the Swiss study. So you see here, these are pictures from those products which contain DKBDE. Yeah, you see most of them black plastic. Yeah, some of this hair, but also tetrabromobisphenol A in different electric products, and hexabromo cyclododecan here in electronic products, and of course in the polystyrene, expanded polystyrene. Then, very important are other screening of the consumer market, like, for example, toys and food contact materials. So often in these black toys, or here you see this coffee cup with the black lid, you find PBDEs at low level, often below 1000 milligram per kilogram, sometimes above 1000 milligram per kilogram. And this shows that these have been made from recycling. Yeah. Some best practice case studies are here from Kashiwara. She analyzed 1100 consumer goods from 18 countries, especially toys. And we have this in a webinar where I will give you also the link at the end. But still further studies are needed, especially, for example, there is no study on UV328 in consumer products or Decloran in consumer products. Looking a bit to transport sector, including textile in the transport sector. So there is only one best practice case study actually on the transport sector in the whole world. Yeah, that has been done also in Japan from Dr. Kashiwara. She analyzed 515 parts indoor of 45 vehicles produced between 1993 and 2012. Also, she used XRF approach and then analyzed in the laboratory. What you see finally, the XRF screening showed that only 32 out of the 500 materials and components contain bromine higher than 0.1%, and only 16 of these contain PBDEs or HBCD above 0.1%. The major components were seed fabric. Actually, most of the high contaminated PBDE materials were the seat textiles you are just sitting on when you are in your car, with direct exposure when you have shorts. Also, there were some soundproof materials and floor coverings, and also some seat polyurethane foam contain high level of PBDEs. And actually, that was a penta-BDE. This was a car from the United States, which have used much penta-BDE. 90% of all penta-BDE has been used in the United States, and partly it has been used here in polyurethane foam in vehicles. And finally, you also find it in Japan. What was also interesting was that the low bromine contaminated samples. So you see that more than 10% had bromine content between 0.01 to 0.1%. And 260 out of 500 samples, this means more than 50% of the samples, had bromine levels more than 5 ppm, 5 milligram per kilogram. This indicates that 50% of interior plastic had a secondary contamination with brominated flame retardants. It is not clear if this mainly comes from recycling or partly come from secondary contamination indoor. This means PBDE can evaporate, for example, from the seat textile and then can deposit on other plastics. Yeah, and over the years, this can increase to levels of more than 5 ppm. But similar comprehensive screenings of cars is needed from other regions, including also other is no monitoring of Decloran Plus and UV328, which we know are heavily used in cars and other transports, but there is no study on these. Also interesting here, and we will hear more in the next presentation from Pierre, is shredding, shredders and analyzing of shreds of live vehicles. Why I bring it here is to show it's very complicated to understand what is the average content of POPs in vehicles. So it's very complicated to different cars and the different plastic parts. You see already the 45 cars in Japan was for sure a study which was longer than half a year. But here, if you take the shredder from a certain cars, then an average can be generated. And I give you here some examples. Also here, good studies from Japan. For example, they shredded cars which are older than 1996 or 1999. And you see also, like for electronics, the levels here in these cars are relatively high, around 80 gram PBDEs per car. But for the cars which were younger than 2000, so they did a specific shredding for cars which were younger than production 2000, only 20 gram of PBDEs were included in average. Yeah, but you see the whole thing is quite complex, and I will tell you more on the complexity of end-of-life monitoring of POPs. Coming to the building and construction sector, in the building and construction sector, major plastics is PVC, expanded extruded polystyrene, EPS, XPS, polyethylene, and polyurethane. The EPS, XPS, and polyurethane in buildings are frequently flame retarded with POPs, including hexabromocyclododecane or PBDEs, but also other hazardous flame retardants like halogenated phosphorus flame retardants. Also, plasticized PVC often contains large amount of additive, up to 60%, including POPs like short chain and medium chain chlorinated paraffins, or restricted phthalates like DEHP or DBP. And I give you a few best practice case studies here for materials. Here I was involved from Beijing University. We screened 124 products on the Chinese market. A high share of the soft PVC, and 50% of PVC is finally going into building and construction. And a large share of the polyurethane foam spray, which fully goes into construction, contain very high levels of short chain and medium chain chlorinated paraffin, up to 50% of the product. And the same was found in Europe. You see here a study on polyurethane foam used also in new buildings. So in the Netherlands, they screened also for chlorinated paraffins, and they found that a range of foams contained up to 50% of medium chain chlorinated paraffins and up to 30% of long chain chlorinated paraffins. Yeah. Additionally, also here, organophosphorus flame retardants is contained, and these materials then are also gassing out these additives and contaminate finally the indoor environment with high levels in house dust. This is a study also contaminating indoor environment from a friend of mine, Professor Vetter, and his PhD student Sprengel. They analyzed kitchen huts, and they found in the kitchen huts where the suction system is high levels of short and medium chain chlorinated paraffins. And then they were looking in the kitchen in different materials where these short and medium chain chlorinated paraffins come from. And finally, they found that a major source were ovens, the baking oven. And the baking oven, they contain PVC cables. The PVC cables contain up to 10 to 15% of chlorinated paraffins. And when you heat the oven, then these chlorinated paraffins evaporate from the cables. and they directly go not only in the kitchen, but they directly go into the food. And Professor Vetter also analyzed that. What was impressive that 50% of 20 of these baking ovens in Germany contain these very high levels of chlorinated paraffins in the indoor of the baking ovens. Here, a best practice study from monitoring of additives in PVC in Switzerland. So they analyzed 150 flooring samples. They determined the polymer type, and only for PVC they were looking. They looked for the phthalates. Range of the phthalates are restricted by REACH regulation. They also analyzed what alternative plasticizers are in, and they analyzed elements like cadmium and lead, which is frequently used as additive in PVC in the past. And they also did biomonitoring for toxicity of extract of these flooring samples. And they found that 16% of the samples contained regulated chemicals above 0.1%, mainly lead and phthalates, this DEHP. Also, they concluded most probably from PVC recycling from older PVC where high amount of lead and DEHP were used. Unfortunately, in that study, they did not analyze the short and medium chain chlorinated paraffins because that analysis is quite complex, and at the ETH at that time, this analysis was not available. So for Tunisia, that would be an interesting study. You could look to your PVC floorings and what kind of additives are there. So also, I give you one study, because I know you had in Tunisia a study about EPS and XPS and HBCD in that material. And in future, there will be the question on EPS, XPS, if in the demolition of a building, if it contains HBCD or not. And a friend of mine from Fraunhofer Institute, Dr. Schlummer, he invented a method, which is a simple testing method, which you can do directly on site. And you do not need to take a sample and bring it to the laboratory and wait 1 week to decide if your samples contain HBCD. So here, what he has done, he has taken an XRF, and then first you screen your EPS, XPS for bromine. If it contains bromine, then you take a little bit acetone and you put your EPS in the acetone, and then EPS shrinks. And if you have HBCD, the HBCD is going into the acetone phase. And if you have the other flame retardant, which is used in Tunisia, this is the polymeric flame retardant. This polymeric flame retardant does not go into the acetone phase. So therefore, in the first step, they analyzed the EPS, and in the second phase, they analyzed and screened with the XRF also the acetone. And you see here, by this method, you can distinguish very easily between here one EPS which contain the polymeric flame retardant. You see here, the PS is bromine positive, but the acetone is negative. Yeah, while for others, yeah, where you have a positive EPS and also a positive acetone phase, you know, okay, this contain hexabromocyclododecan. Unfortunately, today there are more products on the market, and this also includes some additive flame retardants. Therefore, this method need to be refined when you are doing monitoring. There are many more polymers which are flame retardant actually in buildings materials, but there are hardly any study on that. PBDEs have been used frequently, as you have also seen in the Swiss study, but there is actually no study in the whole world about PBDE in products in buildings. Yeah, so therefore we have initiated a year ago now one monitoring study on PBDE in plastics in buildings, where we also did a screening, and these samples are currently analyzed. So this time, unfortunately, I cannot show results. Maybe next time. Yeah. But this kind of monitoring of POPs in construction and demolition is very important. Pierre in the next presentation will show you more, because it is the biggest waste flow in future, also for your country. And in Germany, we had now the first project about what kind of plastic might be recycled from buildings and materials, and also guidance documents have been developed. A last case study, what we have done on monitoring of POPs in plastic and recycling. We have done recyclates in middle and low income countries, which was related to the global monitoring plan. So here in that study, we have sampled 270 plastic pellet samples and 100 shred samples in 3 different world regions. From Africa, we have selected Nigeria and Ghana at that time. From Asia, Mongolia, Vietnam, Thailand, Indonesia. From South America, Brazil, Argentina, and Chile. We have sent the samples to 6 different laboratories: National Laboratory of Japan, Fraunhofer Institute, Germany, Tokyo University, Spanish National Laboratory, the colleagues of Begonia in Barcelona, and the National Material Institute in Thailand. And the different institutes have screened for different POPs. I just show you very few results in a minute. One is on PBDEs. These were found overall in the highest concentration. And you see from these recyclates, we have first screened with bromine. You see here from the 270 pellets, 190 pellets were below 15 milligram per kilogram. Yeah. And this shows nearly 3/4 of all samples didn't contain any brominated flame retardants. Yeah. And this you do not need to analyze. Yeah. And the others we analyzed. So there we found that 9 samples had PBDE concentrations above 1000 milligram per kilogram. Further 3 samples were above 500 milligram per kilogram. And 12 samples further were between 50 and 500 milligram, and then 25 samples were between 15 and 50 milligram per kilogram. What you also see with the colors is that basically only high impact polystyrene and the ABS plastic were above the 500 milligram per kilogram. So you see also here that some flame retardants were very specific in the application of the different polymers. Yeah. Also for this, it would be nice to have more such detailed studies. Some major findings of the studies: the plastic recycling in the assessed low-income country was largely uncontrolled. So therefore, also when you look now in Tunisia about plastic recycling, it's quite interesting to understand what plastic is recycled and what products are produced. So here for our developing countries, we have seen that often from this recycling, it directly went into food contact products or toys or skin contact products. Then PBDEs and short and medium chain chlorinated paraffins were detected in major relevant polymers, sometimes above basal low POP content and also above the unintentional trace contaminant of Europe. Yeah. But major other countries do not have at the moment unintentional trace contaminant. Yeah. So when you think about POPs in products, I think that's the first step. Then Decloran Plus and UV328, we also have screened about 120 samples, and we found that they were frequently below detection limit. So overall, from the 120 samples, only 3 samples contain Decloran Plus above 1 milligram per kilogram, and only 3 samples contain UV328 higher than 1 milligram per kilogram. Yeah, so you see, this is another concentration class compared to the PBDEs, yeah, and the chlorinated paraffins. Also, we analyzed teeth that was analyzed in the Spanish National Laboratory. So they were in the nanogram per kilogram level. And plastic recycling is a field for monitoring and assessment and regulatory control. Currently, major plastic additives have several provisional low POP content in the Basel Convention. So also there for countries at the moment, and maybe you can tell me afterwards if Tunisia already has decided for Tunisia low pop content, but it will be very especially interesting to develop unintentional trace contaminant limits. And also here maybe it's interesting for the science community to think what would be science-based levels in respect to exposure. Of course, POPs are only the tip of the iceberg in recycled pellets. Therefore, in our study, we also, like in the Swiss study, we used bioassays where we evaluated extracts from these recyclates in respect to endocrine effects, in respect to genotoxicity and dioxin-like toxicity. So I think considering the complexity of plastic and plastic recycling, this bioassay approach need to have more attention. And I know, for example, that Nestle, the biggest food producer in the world, they are using bioassays to evaluate the dioxin, the endocrine compounds in their packaging material. And the policy of Nestle is to have no endocrine disrupting effects in their food packaging. So this is now nearly the end. So there's an update of the guidance documents. At the moment, I am working on that, including the POPs listed in 2023 and 2025. This means also UV 328 and Decloran Plus. Also updating international and national standards on analysis of POPs and adding some new case studies. Also, we had in that project from the Global Monitoring Plan, we had a 5-day webinar, each around 3 to 4 hours. And the topic is just to analyze POPs in plastic. Yeah. So now I gave you 45, 50 minutes, but here you have 18 hours of webinars, which is online of the website of the International Panel on Chemical Pollution, where I'm a member. And those which are interested, part 1 is understanding POPs in plastic, part 2 is on sampling of plastic, and part 3 is on extraction, cleanup, and analysis of POPs in plastic. So, depending on the time, Jordi, is the time over? Jordi?
Yes, you can.
Is the time over, or do I have a few minutes left?
It's almost over, but if you have these 5, as the Rainer say, as a German one, you can have 5, but not more, 5, 10. You can continue, Roland.
Yeah. So let's say that's a small addition, and I think it's interesting. It is. Yeah, but it's only a few slides on unintentional POPs in products. Yeah. Also, unintentional POPs are present in a range of chemicals and products such as pesticides, pigment dyes, or food and feed additives, and can enter consumer products, for example, in paints or in the food chain. Europe has recently set a law in unintentional trace contaminant for hexachlorophene in chemicals, mixtures, and products, which is 10 milligram. Currently, Europe is establishing a low unintentional trace contaminant limit for PCBs in mixtures and products and food, and where already gave on the analysis. And also, there are some unintentional trace contaminant limits of dioxins. For example, in Japan has a limit of dioxin in pesticides. So this is a good case study from Japan, which shows PCBs in pigments, yeah, which are used for paints. And Japan has a unintentional trace contaminant of 50 milligram per kilogram, and you see here that there are some pigments up to 2,000 milligram per kilogram of pigment. Yeah, And so in Japan, these pigments are then taken out of the market. Yeah. This is another example. This is tetrachlorophthalic acid or anhydride. This is a high volume product which is used to produce a range of high volume pigments. So here also Japan did a market survey, the Japanese government, and hexachlorobenzene were found up to 3,000 milligram per kilogram. This means 3 grams of hexachlorobenzene in the chemical product, which finally goes also in the paint and pigment, which is partly used also in children toys or in printing products. And this is one of my favorite slides. Overall, it's the historic inventory of dioxin released in the Japanese environment, which showed that actually the biggest pollution of dioxin in the world did not come from open burning or from incineration, but that actually in the 1940s, 50s, 60s, 70s, and 80s, the chlorinated aromatic chemicals released tons of TEQ into the environment. This is here only for Japan. So here in the rice fields, pentachlorophenol pesticide and CNP pesticide every year around 30 kilogram TEQ into the rice field, into the environment. In total, Japan had nearly released a half ton of TEQ into their rice field. And this you can compare to the total release of dioxin in the world of around 100 kilogram TEQ per year. Yeah, the total of India, China, everybody combined, yeah, is 100 kilogram TEQ. Just the aromatics in Japan in the 1960s and 70s were half a ton into the environment. And we have done a monitoring of pesticide in Australia in 2010 in a PhD. And we analyzed around 25 pesticides for dioxins, and all pesticides contained dioxin, all, which we analyzed. Yeah. So this second study here, where I have some data, is from the United States. This is, they have analyzed also 2,4-D for dioxin levels. But what was special is that they have used the instrumental analysis and also a Calux TEQ. This means a bioassay for dioxins. Yeah, you see the correlation was quite nice here for the 2,4-D, but then there were some pesticides where you didn't find any TEQ with the instrumental analysis, but the pesticide, the bioassay, showed very high TEQ. So here, 1,700 picogram per gram TEQ. This is comparable. No, that's per gram, like a fly ash. Yeah, and you see the reason is that they did not contain chlorine; they contain bromine. Yeah, so this means that there were brominated aromatic compounds in these pesticide. Yeah, or here with this nitrogen group, which had actually a very high dioxin-like toxicity, but we would never understand from instrumental analysis. Yeah. So therefore, I think that the dioxin-like toxicity in pesticide would be one of my favorite to screen in countries. And I think there will be a very interesting outcome. Only 3 samples on food and feed. Here, screening of eggs and dioxin-like toxicity. So Brambilla and another study here found high dioxin levels in the eggs. And finally, what was the source? The source was wood. Yeah, and this was recycled wood. Contained pentachlorophenol, and pentachlorophenol is always related to dioxin contamination. So also here, where I said we have wood sampling and wood screening is quite interesting in respect to waste wood. This is a screening from China on copper sulfate. Copper sulfate is an important mineral supplement for animal nutrition. So the last 2 decades, recycled copper is used in copper sulfate production partly. And in China, it was mainly used from recycled copper sulfate. The levels were above the European limits for feed. And the source finally was actually copper sulfate, which were recycled with secondary HCl from various processes from electronic industry. And the dioxin contamination actually came from HCl, because about 2/3 of all HCl, hydrochloric acid, is secondary HCl from industry. And sometimes they come from processes with very high levels of dioxins. Yeah, so here for China, they contaminated the copper sulfate, which were used as a feed additive. Last example, zinc oxide. Also, zinc oxide is partly used as feed additive and food supplement. Zinc oxide can be produced either from virgin ores or can be produced from recycling processes. Here from Dr. Mali's laboratory in 2014, you see very low levels in zinc oxide from virgin ores, but there were zinc oxides detected from a food case in Chile, where they contaminated meat in the worth of $200 million dollars. And the level here was 17,000 nanogram TEQ per kilogram TEQ, sufficient to contaminate the whole meat from Chile. So the source of such highly contaminated zinc oxide is zinc recycling with the Wells process. So after the Wells process, you get zinc oxide, but there you need a very, very strong cleaning if you would want to use this in the food and feed industry. Yeah, thank you for your attention.